So let's solve some questions based upon whatever we discussed yesterday. All right. So this question, a solid sphere is rotating freely about its symmetry axis in free space. The radius of sorry, the radius of the sphere is increased keeping its mass same. Which of the following physical quantities would remain constant for the sphere? A is angular velocity, B is moment of inertia, C is the rotational kinetic energy, and D is angular momentum. So who can tell? Now, what are you doing? You are changing its radius, keeping the mass same. Okay. So now, if you are not exerting any external torque in doing this, something will remain constant. Which is that quantity which remains constant? Angular momentum, right? So it is option D. This is the answer. Okay. Two disks of same moment of inertia rotating about their regular axis. So we have two disks, they have same moment of inertia, okay, and they are rotating about the regular axis. That means an axis which passes through their center of mass, okay, and it is perpendicular to plane of the disk. They have angular velocities omega 1 and omega 2. They are brought into contact face to face, coinciding the axis of rotation. So they are kept on each other. Okay. So this is first disk, you can say. Okay, this is second disk. They were rotating with some angular velocities. Okay, omega 1, omega 2, and the moment of inertia is same. Okay, now they are kept on each other. What will happen? So this is like collision. Okay, but there is no external torque. If you think about system of these two bodies only, there is no external torque that is acting. So you can say the angular momentum will be conserved. Okay, so question is the expression for loss of energy during this process. So what will be loss in kinetic energy? That's what we have to find. So now you can say L1 plus L2. Okay, total angular momentum before the collision equals to total angular momentum after the collision. So I times omega 1 is angular momentum of first disk plus I times omega 2. This is the angular momentum of second disk. It's equal to. Now, when you keep those two disks onto each other, the total moment of inertia will be what? 2I. Okay, so total moment of inertia will be 2I. And we don't know about the angular velocity. We have to find it out. So let's suppose angular velocity is omega. Omega final, you can say. Or let's call it omega only, because for initial angular velocities, it is omega 1 and omega 2. So I gets cancelled, right? You can take I common and cancel it out. Okay, then you take the 2 on the other side. So you get omega equals to omega 1 plus omega 2 divided by 2. Okay, so loss in kinetic energy, let's call it delta K. It is K initial minus K final. So it is half of, okay, I into omega 1 square. This is initial kinetic energy of first body, plus half of I into omega 2 square. This is for second body. Okay, this is the total initial kinetic energy, minus it is half of moment of inertia of two bodies. Okay, final moment of inertia is I multiplied by omega square, right? So now, can I add a page here? So we want to find out the change in kinetic energy. Okay, the difference in kinetic energy. So now, how much is omega? It is omega 1 plus omega 2 divided by 2. So meanwhile, this 2 and 2 gets cancelled out, right? 2 and 2 gets cancelled out. So this is equal to, you can say it is half of I omega 1 square plus half of I omega 2 square minus minus I into omega square. Okay, I multiplied by omega square, which is omega 1 plus omega 2 divided by 2 square. Okay, so now let's square this. So we get half of I omega 1 square plus half of I omega, this was 2, omega 2 square minus, this is, if we square this, it will be omega 1 square plus omega 2 square. Okay, so it is 1/4. If you square this 2, it will be 1 by 4. Right, 1 by 4 I multiplied by omega 1 square. I will just expand the terms, right? Minus 1 by 4, sorry, 1 by 4 I multiplied by omega 2 square, and minus you will have 1 by 4 multiplied by I multiplied by 2 times of omega 1 into omega 2. Okay, this is what we'll have, right? So then you can subtract this out. So you will get, this is half of I omega 1 square minus 1/4 of I omega 1 square. So 1/4 of I omega 1 square will remain, right? Half minus 1 by 4 is 1 by 4. So 1/4 of I omega 1, 1/4 of I omega 1 square. Similarly, you will have half of I omega 2 square minus this 1/4 of I omega 2 square will be plus 1/4 of I omega 2 square, and minus you have 1/4 of this thing. Okay, 2 times I omega 1 multiplied by omega 2. So you can take 1/4 common, right? 1/4 common, and I also you can take common. Okay, so it will be omega 1 square plus omega 2 square minus 2 times omega 1 into omega 2, right? You will have that. Okay, yeah, so you will have that. So you will get 1/4 of I am taking common, it is omega 1 square plus omega 2 square minus 2 times I omega 1 multiplied by omega 2. So this thing is omega 1 minus omega 2 square, right? So we have 1/4 of I multiplied by omega 1 minus omega 2 square. This much is the loss in kinetic energy, right? Okay, so it is option A. Option A is the answer. So is it clear, or is there a problem? Two rotating bodies A and B of masses m and 2m with moment of inertia IA and IB is greater than IA, have equal kinetic energy of rotation. If LA and LB be their angular momenta respectively, then, okay, this is very simple. Tell me which is the answer. See, they have equal kinetic energies. So Ka equals to Kb, right? Okay. So after that, what's given? IB is greater than IA. Moment of inertia of second body is greater than first body. Okay. So it is half of IA multiplied by omega A square. Okay. It's equal to half of IB multiplied by omega B square. Okay. So now half and half you can cancel out. So then what you can do is you can do the same trick that we had done earlier. So you can multiply and divide by IA. Okay, so this will be IA omega A whole square divided by IA. It's equal to IB omega B whole square divided by IB. Okay, right? So what is this thing? This is angular momentum of first body. Okay, this is LA. LA square upon IA equals to LB square upon IB. That's what you have. Okay, so then you can write LA by LB square. I mean, you will take this on the other side. Okay, so it's equal to IA upon IB, right? If you take this IA on right hand side. Okay, so now if you take square root, it will be square root of IA by IB. You answer option C. Okay, what is option C? LB is greater than LA, right? Exactly, because IB is greater than IA. Okay, you have LA upon LB square equals to I upon IB. So this thing will be less than 1. Okay, this thing will be less than 1 because IB is greater than IA, right? So then you can take LA upon LB, it's equal to square root of IA upon IB. This is less than 1 because IB is greater than IA. Okay, therefore the square root will also be less than 1. So LA upon LB is less than 1. Take LB on other side. So you get LA is less than LB or LB is greater than LA. Option C. Two disks are rotating about their axis, normal to disks and passing through the centers of disk. Disk D1 has 2 kg mass and 0.2 meter radius and initial angular velocity of 50 radians per second square. Disk D2 has 4 kg mass, 0.1 meter radius and initial angular velocity of 200 radians per second. Two disks are brought in contact face to face with their axis of rotation coincident. The final angular velocity of the system is. This is simple. Okay. So angular momentum is conserved when you keep two disks one on the other. Okay. I1 omega 1 plus I2 omega 2 will be equal to what? I1 plus I2 multiplied by omega. Okay. So total initial angular momentum, because the disk were separate. Okay. So angular momentum of first one is I1 omega 1. Angular momentum for second one is I2 omega 2. Now you are keeping the one on other. Okay. You are combining them. So total moment of inertia will be I1 plus I2, right? And angular velocity is suppose omega. Okay, so angular momentum will be I1 plus I2, which is moment of inertia multiplied by omega. Okay, then these are disks. So how much is moment of inertia? I mean, what's the formula for this? Moment of inertia about an axis passing through the center of mass. It is half of m into r square, right? So it is half of m1 r1 square omega 1 plus half of m2 r2 square omega 2. Okay, it's equal to I1 plus I2. So you can take half common, m1 plus m2, sorry, m1 r1 square plus m2 r2 square. Okay, it is mr square upon 2, right? I have taken that 2 outside, and omega is what we have to find out. Okay, so half gets cancelled out. Okay, then sorry, we can substitute the values here. So how much is m1? M1 is 2. So it is 2, sorry, 2 multiplied by R1 is 0.2, 0.2, or let's do one thing. Let's write omega equals to M1 R1 square omega 1 plus M2 R2 square omega 2 divided by M1 R1 square plus M2 R2 square. Okay, if you take this bracket on the other side, right, then we can substitute for the values. So it is m1. How much is m1? It is 2 multiplied by r1 square is 0.2 square. Omega 1 is 50. Oh, this page won't be sufficient, right? So here we'll substitute the values, right? So m1 is how much? It was 2. Okay, m1 is 2, r1 is zero point 0.2, and omega 1 is 50. So it is 2 multiplied by 0.2, sorry, 0.2 square multiplied by 50 plus m2 is how much? M2 is 4 multiplied by zero point 0.1, okay, square multiplied by 200. So 4 multiplied by zero point 0.1 square multiplied by, what was it, 200. And in denominator we have 2 multiplied by zero point 0.2 square, so 2 multiplied by 0.2 square plus 4 multiplied by 0.1 square. Okay, so we have to do all this calculation. So 0.2 square, it is 2 multiplied by 10 raised to minus 1 square, which is 4 times 10 raised to minus 2. Okay, so this is 4 multiplied by 50. Okay, let's do that. So 4 into 10 raised to minus 2 multiplied by 50 plus this thing is just 10 raised to minus 2, right? Because 0.1 means 10 raised to minus 1. So 4 times 200. Okay, it is 800 multiplied by 10 raised to minus 2. And in denominator we have again the same thing. It is 4, 2 times 4 into 10 raised to minus 2 plus 4 multiplied by 10 raised to minus 2. So 10 raised to minus 2, we can take it common and cancel it out throughout, right? And then it is just 50 times 2 is 100. Sorry, 50 times 4 is 200. 200 times 2 is 400 plus 800 divided by, we have 4 times 2, how much, 8, 8 plus 4, 12. So it seems 1200 divided by 12. Okay, right? So omega equals to 100 radians per second should be the answer. All right, let's check whether we have got, yes, option B is the answer, 100 radians per second. So this one was straightforward, just some calculations, right? Okay, let's see next one. Okay, when I'm adding a page, it is getting copied. Okay, next one. A circular platform is mounted on a frictionless vertical axle. So there is a circular platform which is mounted on a frictionless vertical axle. Okay, its radius r is equal to 2 meters and moment of inertia about 200 kg per meter, sorry, kg meter square. It is initially at rest, so that platform is at rest. A 50 kg man stands on edge of the platform and begins to walk along the edge at the speed of 1 meters per second relative to the ground. Time taken by man to complete one revolution is, okay. So what is given? This is nice question. It's from mains. There is this platform, circular platform, okay, and this is an axle. Okay, this is an axle, or you can say it's axis of rotation, right? So then there is a man who walks on this platform. So when he will walk on the platform, what will happen? Can you guess? Yes. Can you guess what will happen? So let's suppose the man walks in anti-clockwise sense. Okay, so it's given that the platform is initially at rest. 50 kg man stands on the edge of the platform and begins to walk along the edge at the speed of 1 meters per second. So he walks like this along the edge. Okay. So the platform will move in opposite direction. The platform will rotate, right? Yes, no. See, initially the man and the platform, they were at rest. Okay. So total angular momentum was zero. Now when man begins to move, okay, when man begins to move along the edge of the platform, what happens? There will be some angular momentum, okay, associated with the man. So when he moves in forward direction, he is pushing that platform in backwards direction, right? And because of, sorry, sorry. So because of this, see, the man is moving like this in forward direction. So platform gets a push in backwards direction. And because of that push, now the platform will rotate. Yes, no, because it is mounted on that axis of rotation. It is mounted on the axle. Can you imagine this? Yes, no? All right, good. So now what can we say about this rotation? So initially both were at rest. Okay. So angular momentum of platform and angular momentum of the man was zero initially. Afterwards, suppose L suffix m is the angular momentum of man and L suffix p is the angular momentum of platform. So how will you find out angular momentum of man? Now man is performing circular motion. So his angular momentum is what? It is moment of linear momentum, r multiplied by, okay, it is r multiplied by linear momentum, which is m into v, right? Okay. And angular momentum of this platform, which is disk actually, it is I into omega plus I times omega. Okay. So now we can find out how much is this angular momentum. So let's move this on left hand side. So we get I times omega. Okay, I times omega equals to what? Minus r multiplied by m into v. So how much is I? I is half of m into r square. So how much is its mass? So small m is mass of man. Let's call mass of ring. Okay, m is mass of ring. It's 200 kg. Okay, sorry, not ring. I'm sorry. So this m is mass of disk. It is 200 kg. Or the moment of inertia is given. Sorry, moment of inertia is given. Okay, moment of inertia is disk. Moment of inertia of the disk is directly given, right? So now we can find out omega. Okay, so omega will be equal to what? Minus of rmv divided by I. So now we can substitute the values. R is how much? R is 2 meters. M is 50 kg. And he is moving with the angular velocity of how much? Sorry, with the velocity of 1 meters per second squared. So 1 divided by I is 200. It's given. Okay. So what do we get? We get 2 into 50 is 100. 100 divided by 200 is 1 by 2. Okay. So this is minus 1 by 2. Okay. Radians per second squared. So what will this minus 1 by 2 mean? It means that when man moves in this direction, okay, the disk will move in the opposite direction, right? Yes, no? All right. So then the question is time taken by man to complete one revolution. Okay, see, now it's like two objects are moving towards each other. So let's suppose man starts from this point. Okay, man is moving in this direction, the disk is moving in opposite direction. Okay, so if only the man was moving, we could find out the time very easily, right? What could be the time? If disk was stationary, then it is just 2 pi r divided by, okay, see, v equals to 2 pi r divided by t, right? So t will be equal to what? 2 pi r divided by v. Okay, so if just man was moving, this could be the time period. Now disk is also moving in opposite direction. So what do we have to find it out? Find out the velocity of man with respect to disk, right? The velocity of man with respect to the disk. Okay, so let's do that. So now, how much would be the velocity of any point on the edge of this disk? Okay, we can say velocity of the point at edge of the disk, because this is what matters, right? Only the point on edges, the points on circumference of the disk, they are coming towards man. Okay, so it is r times omega, right? So velocity of disk, we can say it is r times omega. So it is r multiplied by omega of the disk. Okay, which we found out. So r is 2 meters, omega is minus half. Okay, omega is minus half, right? So what do we get? Okay, so this is minus of r is 2, omega is, this is 2 times, okay, omega is minus half, right? R is 2, omega is minus half. So it is minus 1 meters per second, you can say. Okay, so now the time period will be equal to, or here the relative velocity of man, okay, with respect to the disk is equal to what? It is velocity of man minus velocity of disk. Okay, velocity of edge of the disk, you can say, or circumference of the disk, because man is moving on circumference only. So circumferential points of the disk, they are coming towards man. Okay, so it is 1 minus this minus 1, or you can say it is 2. So time period will be equal to what? 2 pi r divided by velocity of man with respect to the disk. Disk meaning the circumference of the disk, circumferential points of the disk. They are moving, okay, towards the man, right? So it is 2 pi multiplied by r. How much is r? It's 2 divided by this 2. Okay, so 2 gets cancelled. 2 pi should be the answer. 2 pi, yeah, option C. 2 pi seconds should be the answer. So is it clear? Circular disk of moment of inertia I suffix t is rotating in a horizontal plane about its symmetry axis with a constant angular speed omega I. Okay. Another disk of moment of inertia IB is dropped coaxially. So this is similar, okay, onto the rotating disk. Initially, the second disk has zero angular speed. Eventually, both the disks rotate with constant angular speed omega f. The energy lost by the initial rotating disk to friction is, okay, due to friction is. So this is similar, right? We have recipe to solve this. So let's solve this. So moment of inertia of first one is it, moment of inertia of second one is ib. Okay, and initially only the first disk is rotating. So you can say, sorry, The initial angular momentum, total initial angular momentum is equal to total final angular momentum because there is no external torque. So how much is initial angular momentum? L initial equals to L final. Okay. So it is just IT multiplied by omega I. Okay. Omega I is its speed. Okay. Angular speed. So it's equal to. Then another disk of mass IB, sorry, moment of inertia IB, it is dropped onto the first. So now moment of inertia is IT plus IB and the angular velocity becomes suppose omega. So their angular velocity is omega. Okay. So from this we can find out omega equals to what? It is IT divided by IT plus IB multiplied by omega I. Okay. And we want to find out energy lost. Okay, so let's add a page. Let's rotate the page. Okay. So initial kinetic energy is, so how much is energy loss? So delta K is initial kinetic energy minus the final kinetic energy. So initial kinetic energy is half of I suffix T multiplied by omega I square minus final kinetic energy is half of I is now IT plus IB. Okay, and how much is omega? Omega is this thing, IT upon IT plus IB multiplied by omega I. So IT divided by IT plus IB multiplied by omega I, and we have square of this because this is final angular velocity, right? So half of I multiplied by omega square is kinetic energy. So now uh, final moment of inertia is IT plus IB. Final kinetic energy is, sorry, final angular velocity is this thing. Okay. So then we have to solve this. So this IT plus IB square we have, it gets cancelled with this thing. So we'll have only IT plus IB in denominator. So we are left with half of IT to omega I square minus half of IT, no, it will be IT square omega I square divided by IT plus IB in the denominator. Okay. And then we have to do some simplification. We can take this whole term common. So we can take half of IT multiplied by omega I square common from both the terms. Okay. So we are left with 1 minus. So from here it is IT upon IT plus IB. Okay. Then we can make the denominator same. So here we'll multiply and divide by IT plus IB. Okay. So it will be this term, the first term. Okay. This thing multiplied by IT plus IB minus IT. IT plus IB minus IT, and in denominator we have IT plus IB, right? So IT and IT gets cancelled out. IT and IT gets cancelled out. So it is IB upon IT plus IB. Okay, so IT times IB. So we get IT times IB upon IT plus IB multiplied by omega I square. This is the loss in kinetic energy. Okay, so nothing difficult, right? Nothing difficult. So where is the, oh, this one. Option D is the answer. Okay, so this is, we have recipe. and we are following the recipe. That's it. Okay. A thin circular ring of mass m and radius r is rotating about its axis with constant angular velocity omega. So when it is said that about its axis, it means that about the natural axis, which passes through the center of mass and it's perpendicular to the plane. Okay, plane of the body. So this is the ring. Okay, what is its axis? It is this perpendicular axis. Okay, this perpendicular axis. Right. It passes through the center of mass. Okay, so then two objects, each of mass small m, are attached gently to the opposite ends of diameter of ring. So two masses are connected here. Okay, so two masses are connected gently here. Okay, so those masses will also begin to move along with the ring. The ring now rotates with angular velocity given by. This is straightforward, very simple question. So initial angular momentum equals to final angular momentum, right? So initial angular momentum was moment of inertia of this, moment of inertia of, sorry. So initial angular momentum equals to final angular momentum. L initial equals to L final, you can say. Initially there was that ring only. So I of the ring multiplied by omega of the ring, that's omega only, equals to, okay, final angular momentum is I of ring plus moment of inertia of these two masses. So that will be 2 times masses, mass is small m, right? Mass is small m. Okay, m multiplied by r square. Okay, mr square multiplied by omega final. Okay, and we have to find out final omega only. So I of ring is what? It is capital M into r square. So capital M into r square multiplied by omega equals to capital M into r square. No, it is the same r, small r square, right? Plus this 2 small m into r square multiplied by omega f. So this r square gets cancelled out. Okay, r square, r square, r square, you can take common and cancel it out. Okay, so omega f is equal to, on left hand side you have m and you can take this m plus small 2m. Okay, on that side it goes in denominator. Okay, multiplied by omega. So option B is the answer. Very simple, straightforward. A round disk of moment of inertia I2 about its axis perpendicular to its plane and passing through its center is placed over another disk of moment of inertia I1 rotating with an angular velocity omega about the same axis. So there is a disk whose moment of inertia is I1, it's rotating about some axis, okay, and another disk of moment of inertia I2 is kept. The final angular velocity of the combination of disks is, oh, this is great, just similar to last question, right? So L initial equals to L final because there is no external torque. Okay, so L initial is what? I1 multiplied by omega. L final is what? I1 plus I2 multiplied by final angular velocity is omega f. And now take I1 plus I2 on left hand side. So you get omega f is equal to I1 upon I1 plus I2 multiplied by omega. Okay, so option A. This was simplest one. Let's see. Oh, this is I1. Sorry. This is C. Right. A thin circular ring of mass m and radius small r is rotating about its axis with constant angular velocity omega. Four objects. So earlier it was two, now there are four objects. Are kept gently to the opposite ends of two perpendicular diameters of ring. The angular velocity of the ring will be. So who can just observe and tell me? Just observe and tell me which would be the answer. Right, exactly. It will be option B. Okay. So that's, do you agree or we need to solve this? So option B is the answer for this. Okay. Let's solve next one. A disk is rotating with angular speed omega. If a child sits on it, what is conserved? Again, this is repeated. Tell me. Right. Angular momentum is conserved. Okay. Because there is no external torque of on system of these two bodies. So angular momentum is conserved. Now instantaneous angular position of a particle rotating, sorry, the instantaneous angular position of a particle on a rotating wheel is given by this equation. The torque on the wheel becomes zero at, okay. So tell me, what should we do? Tau equals to I multiplied by alpha, right? So we are given with theta. So if we take d theta by dt, what do we get? We get 3 multiplied by 2, okay. This is 2t cube. So 3 multiplied by 2 into t square minus 6 multiplied by derivative of this t square is 2 times t. Okay, so 6 t square minus 12t. So this is omega. Okay, if we take d theta by dt, and alpha is equal to d omega by dt. So that is, if we take derivative of this, it will be 6 multiplied by 2t minus derivative of this will be just 12. So when torque is 0, the I cannot be 0. I means moment of inertia cannot be 0. Alpha has to be 0. So alpha is 0. So 12t equals to minus 12 is 0. Okay. Therefore t is equal to what? 1. 1 second. This is the answer. Right? Next question. A wheel has angular acceleration of 3 radians per second squared and an initial angular speed of 2 radians per second. In a time of 2 seconds, it has rotated through an angle of, tell me, angular acceleration is given, then angular speed is given, initial angular speed, and time is given. So this is second kinematic equation. Theta equals to omega naught multiplied by t plus half of alpha into t square, right? Just like s is equal to ut plus half at square. Okay, so omega naught is given, it's 2 multiplied by time is 2 plus half of alpha is 3 multiplied by t square, it is 2 square. So 4 times what? This will be 4 divided by 2. So 2 times 3 is 6. Okay, so 4 plus 6, 10. 10 radians is the answer. Very simple, right? So let's see next question. A wheel having moment of inertia 2 kg meter square about vertical axis rotates at 60 rpm about this axis. Torque which can stop the wheel's rotation in 1 minute would be. So we know tau is equal to I times alpha. Okay, alpha we can find out. It is omega final minus omega initial. Okay, omega 0 divided by time. Okay, so what is omega initial? So omega 0 is 2 pi multiplied by f0. Okay, so it is 2 pi multiplied by f is 60 rpm. So that is 60 by 60 rps, right? 60 revolutions per minute. That means how many revolutions in a second? One revolution in a second, right? 60 by 60. So it is 2 pi radians per second. Okay, so this is equal to omega final is 0. It is stopping. Okay, so omega final is 0 minus we have 2 pi divided by time. How much is time? 1 minute, meaning 60 seconds. Okay, so it is minus 2 pi upon 60, or you can say pi upon 30. So alpha is minus pi upon 30 radians per second square. And tau is I alpha. So tau is I into alpha. So I is 2 multiplied by, you have minus pi by 30, which is, okay, pi by 15. Okay, minus pi by 15, right? Newton meters. This would be the answer. Okay, so option C is the answer, right? So negative sign is because torque is acting so as to stop the wheel. That's why we have negative sign. So let's move on to the next question. A rope is wound around a hollow cylinder of mass 3 kg and radius 40 centimeter. What is angular acceleration of the cylinder if rope is pulled with a force of 30 newtons? So if you pull the rope with, see, you have what? A hollow cylinder. Okay, it's a hollow cylinder like this, and a rope is wound to this cylinder, a hollow cylinder. Okay, so there would be this rope is wound like this, and you pull this rope. Okay, you pull this rope with some force, not some force, with a force of 30 newton. Okay, so F is given, F is equal to what? 30 newtons. So when you pull this rope, what will happen? There will be a force, tangential force acting on this cylinder. Okay, and due to which there will be torque. Okay, there will be torque. So how much would be torque? So this is R. Okay, so torque will be equal to what? R multiplied by F multiplied by sine theta. So how much is sine theta? Because R and F are at 90 degrees. Force is tangential. So angle is 90 degrees, right? So sine 90 is 1. So R times F will be the torque. Tau is just equal to R multiplied by F. Okay, and you want angular acceleration. So you can write it as, okay, tau is I alpha, which is equal to R times F, and therefore alpha is equal to RF divided by I. So what is its moment of inertia? Moment of inertia of hollow cylinder is, what is the formula? It's mr square, right? Okay, so R times F. So this R and R gets cancelled out. F upon mr. So alpha is F upon mr. F is 30, m is 3, and R is 40 centimeters. That means 0.4. Okay, or let's write it as 4 into 10 raised to minus 2 in meters. So this is 30 divided by 3 is 10. Okay, you take 10 raised to minus 2 in numerator, it becomes 10 raised to plus 2. So 10 times 10 raised to plus 2. This is 1000 divided by 4. How much? Okay, so then yes, it will be 100 divided by 4. Okay, so 25 radians per second square. This is the answer. Okay, option B is the answer.